Hello and welcome back. So in the previous class we looked at the Rankine cycle and we also looked at problems related to the Rankine cycle. We will go on now to a cycle which is used for gas turbine engines. This picture shows here the picture of a turbofan engine, the kind of engine which is commonly used on aeroplanes these days. You also see a person here, so you see that the engine is fairly large. This is an engine by Pratt & Whitney, which develops a thrust of about 360 kilonewtons. So, fairly large engine, and you see the diameter of the fan is about 2.8 meters. You can quite comfortably walk in through it if it wasn't running. When we look at one of these engines, we have here a picture of this engine from the book by Turns. So, we see that you can initially have a diffuser section. So, this is attached to a plane, the plane is moving. You can have a diffuser section so that it sort of slows down the air and increases the pressure. Then you have compressors. The pressure outside is low. We have gas turbines used in two main categories of engines. One is on planes in order to propel the plane forward. The other is on land in order to produce power. So, if you were, for example, flying in the air, the pressure outside as you go away from the earth's surface reduces. So, you could have a diffuser to increase the pressure, you would have a compressor to further increase the pressure with multiple stages, and then you have the high pressure air and you add fuel to it and then you burn the fuel. So, for example, you can use aviation kerosene, burn it, and then you get hot products of combustion. These gases now have high enthalpy because you have added heat by burning. And this high pressure, high temperature gas, you can expand it partially through a turbine and remaining you can send out through a nozzle. When expanding it, you get work by expanding in a turbine. That work which you get can be used to run the compressor at the inlet. So, if you expand a little bit of it and send out a lot of it through a nozzle, you can have a jet engine, or if you expand more of it and then use a fan in front to run like this, you can have what is called as a turbofan engine. So, what we are going to do is to look at this cycle. In the real engine, this is essentially an open cycle because you have gas coming here and you have exhaust going out. But what we are going to assume is that instead of doing this combustion here and burning fuel, we will add heat, because that would give us an ideal cycle which we can work on in a cyclic process. So, that cycle is essentially what we call as the air standard cycle, or the basic is air standard Brayton cycle or the Joule cycle. We are talking of air standard cycles because in the real case we have fuel which is burnt and it goes out as exhaust. But in our theoretical assumption of the cycle, we have an ideal cycle where the process is being undergone by air. So, we have air which is here at some point 1. We send it to a compressor. The compressor takes in this air at low pressure, increases its pressure and temperature, and we get air out at point 2. We take this air, in reality we would add fuel here and burn, but in our standard cycle what we do is we add heat here and increase the temperature of the air. So, at the end of the heat exchanger we are still left with air, whereas in this case we would have had products of combustion. So, in our air standard Brayton cycle, we are still left with air after heat addition. So, this is heat addition instead of combustion. We add heat at constant pressure and then we are sending this high pressure, high temperature gas into a turbine where it expands and gives us low pressure, low temperature air. In the process of expansion, we can get work from a turbine. Some of that work is used to run this compressor. The rest of this work is available for us to use for something else, to either propel the vehicle or, for example, to convert it into electrical power to use for producing electricity. This low pressure, low temperature, it is just relatively low temperature air is now sent to a heat exchanger where we reject heat and it still becomes at lower temperature. The pressure remains same ideally in this process 4:1, but the temperature further drops and we are left at point 1 and we can do this in a cyclic fashion again. So, this is essentially what we see. So, the idea here also is that we saw that if we wanted an ideal cycle, we would like to have the Carnot cycle, where we would like reversible adiabatic compression and expansion into 1, 2 and 3, 4, and we would like isothermal heat addition in 2, 3 and 4, 1. We discussed earlier also that isothermal heat addition is not really feasible. So, what is feasible is isobaric heat addition. So, if we take this Carnot cycle and now modify it, what we can do is we can try to still get 1 to 2 as reversible adiabatic or isentropic compression, but instead of adding heat at constant temperature, what we can do is add heat at constant pressure. Then expansion we still have from process 3 to 4. Now, instead of rejecting heat at constant temperature from 4 to 1, we can reject heat at constant pressure from 4 to 1. So, if we do that, instead of having 2 isotherms and 2 isentropes as in the Carnot cycle, we are now left with 2 isobars and 2 isentropes, which now give us the basic Brayton or the Joule cycle. So, this is essentially the cycle we can sort of realize in some sense instead of the Carnot cycle, which is difficult to realize. When discussing these cycles earlier, we discussed not these cycles, when we discussed the TS diagrams earlier, we found out the equation of various lines on the TS diagram. Of course, isentropic lines are vertical lines parallel to the T axis. Isothermal lines are horizontal lines parallel to the S axis. We discussed that if you look at constant pressure lines, they have a slope which changes based on the temperature, and we saw that at higher temperature the slopes are higher. So, we saw also that these lines 2 to 3 and 1 to 4, which are both isobaric lines, will diverge. So, that is something we should keep in mind. These are not parallel, 2 to 3 and 1 to 4 are not parallel. Some books show them wrongly as parallel, but you should keep in mind they are actually diverging. What we can also easily show is that if they were parallel, then the efficiency of the cycle would be 0. So, that is not something which we see or want. So, what we see is that we get a cycle with 2 constant pressure lines and 2 isentropic lines. So, 1 to 2 is smaller than 3 to 4, these lines are diverging. The same graph when plotted on a PV diagram would look something like this. So, over here 2 to 3 is constant pressure, so it is parallel to the V axis, 1 to 4 is constant pressure parallel to V axis. These lines 1 to 2 and 3 to 4 are essentially adiabatic and reversible. So, they follow for an ideal gas an expression of the form PV to the power gamma equal to constant. Those also are diverging. So, we see this would be the Brayton cycle on a PV diagram, and this would be the Brayton cycle on a TS kind of a diagram. This would be the ideal cycle. Like with all the other cases we have discussed so far, if we had a real cycle, then the process 1 to 2 in a real cycle, the process 1 to 2 may not be isentropic. If it is not isentropic, then in the cycle the entropy would increase. So, if it is not isentropic, instead of 1 to 2 which is a constant entropy here, you may end up with some 0.2 prime, let us say, which is to the right, because entropy increases, so it has to move to the right. It is adiabatic but irreversible, so we will have a 0.2 prime to the right. Similarly, in the process 3 to 4, we expect the entropy to remain same. It is adiabatic and reversible, so we expect it to be like this. But in the real case, we may have an adiabatic process which is not reversible. So, it is adiabatic, so the entropy cannot reduce. It is irreversible, so the entropy increases. So, what in that case would happen is, if we are expanding to the same pressure, we would reach with some other point 4 prime over here, which has an entropy to the right. So, we see going 2 to 2 prime, the entropy goes to the right, entropy increases. Instead of 3 to 4, if you go to 4 prime, we still go to the right because entropy still increases. So, we may have a real cycle of the form 1, 2 prime, 3, 4 prime, where we can find out, if we know the isentropic efficiencies, we can find out the amount of work done from the ideal process and the isentropic efficiency. This process 1 to 2 prime is irreversible. We do not know what it looks like. We cannot find, you cannot take its area and find anything. But if we know the value of, say, entropy and temperature at 2 prime, then we can find out what was the work done in terms of the isentropic efficiency and the ideal process 1 to 2. That is something which we see. In all of these cases, one of the things we discussed earlier also is, why are we doing things in a cycle? So, we discussed, for example, that if you have, I am just going to maybe take some space here to draw something. We discussed earlier at some point of the course that the reason we run these things in a cycle is that, for example, if I have a piston cylinder arrangement of this kind, I can expand this to get some amount of work. So, what happens after I finish expansion? Then I cannot get any work anymore. I need to further expand to get some more work. So, then the idea here is, if I want to use the same piston cylinder arrangement, for example, I need to bring this back to the bottom. I need to bring this to the left. So, how do I bring this back to the left? So, the way to bring this back to the left is, I must reject heat so that the volume reduces. So, I have some gas. If I add the heat to it, the volume increases. So, this piston goes, for example, from here to somewhere here, and this amount of work I can extract. Let us say it is at constant pressure, then the integral of PdV would give me the work done if I was doing a piston cylinder arrangement. Once I have reached this point, if I want more work, I need a bigger cylinder. So, essentially, if I want continuous work, I need an infinitely long cylinder so that I can keep adding heat and it keep expanding. But that is not feasible. I cannot get an infinitely long cylinder. So, then what I need to do is bring this back here so that once again I can expand it. So, how do I bring it back here? If I want to bring it back here, I need to reject heat so that this goes to the left. So, essentially what we see is that in order to do this in a cyclic fashion, we need to keep rejecting heat, because when we add heat, we can get expansion and we can get work. In order that we can expand once again, we need to usually bring back this thing to the original state, which means in that process we are rejecting heat. So, that is essentially what we see. But instead of using a piston cylinder arrangement here, what we are doing in these cases is we are using a flow volume, where we are changing the cross section of the volume and changing the components which are there, so that the gas undergoes these processes in various components, but without actually physically changing the volume of having a displacement of the volume. So, we do not have a piston cylinder kind of arrangement here, but we are changing the cross section and we are changing the area occupied by various components, and in that process we are making the gas go through all of these processes. So, that is essentially what we are doing. So, we can look at some expressions in these cases. They are all written here, but what it is easier to do in most of these cases is to just derive them, because we are always using just those 3 or 4 initial equations which we have. So, the first law, as always, for a control volume is given in this form. You have sigma mi dot if there is more than one inlet, but we usually do not have that here. Kinetic energy, or V square by 2 plus Gzi minus m dot E into the similar kind of term is what we would have. If we had to look at the compressor, 1 to 2 happens in a compressor, 3 to 4 happens in a turbine, 2 to 3 and 4 to 1 happen in heat exchangers. In the turbine, if you were to look, for example, 3 to 4, it is usually a steady state process. This is 0. It is adiabatic. This process happens fast. So, this is 0. There is work done which we want. usually the changes in enthalpy are much higher than changes in kinetic energy. So, these terms and the corresponding terms which would have been here would be 0. So, we are left with work done is equal to enthalpy at the inlet minus enthalpy at the outlet. So, Wt is enthalpy at the inlet, turbine inlet is at 3, exit is at 4. So, work done is essentially H3 minus H4. In a similar fashion, for the compressor work done would be enthalpy at the inlet of the compressor minus enthalpy at the outlet of the compressor, which is essentially H1 minus H2. If I want the positive value, I say mod of Wc and take it as H2 minus H1. The formula gives us this value would be negative, sorry there is no dot here, this would be negative. So, I am taking the mod of it and writing it as H2 minus H1. For the heat exchangers, this remains and this is 0. So, we are left with the heat transferred on a specific basis. In addition to this, of course, we also have dm by dt is m dot I minus m dot E, and these are steady. So, this is 0. So, we are calling m dot I equal to m dot E equal to some m dot. We have been doing this several times, and if we can divide by m dot. For the heat transfer, we see that this is essentially exit enthalpy minus inlet enthalpy, because these two go to the other side. So, the heat transferred in process 2 to 3 is essentially enthalpy at the exit minus enthalpy at the inlet, which is H3 minus H2. The heat is coming in here, Q in, heat is going out here. 1 to 2 and 3 to 4 are adiabatic, there is no heat transfer possible. The Q out is again enthalpy at the outlet minus enthalpy at the inlet. So, Q for the process 1 to 4 or 4 to 1 would be H1 minus H4, enthalpy at the outlet minus enthalpy at the inlet. This value would be negative, because enthalpy, there is heat rejected over here. This is at a lower temperature compared to 4. So, the value here would be lower, this would be negative. So, the mod of that is essentially written H4 minus H1, which would, we are just writing the positive value here. So, W net is essentially sigma W, which is work in 3 to 4 plus work in 1 to 2. This would be positive, this would be negative. It would come out as a difference of two quantities. Since we know that already, we can write it as essentially Wt minus mod of Wc. From the first law, we also know that W net is equal to Q net. For first law for a cyclic process, there is no change in internal energy, because we reach back to the same point always. So, this is true. So, we can also write this as Q net. So, the efficiency is the net work divided by the heat input. So, or net work is equal to net heat. So, we can also write this heat input is what we are giving in process 2 to 3. The same way we have been writing earlier. So, Q net is actually sigma of all Q, but we know that Q in is positive, Q out is negative. So, we can write this as 1 minus Q in minus mod of Q out divided by Q in, and when you divide by the Q in, we get 1 minus Q out by Q in. So, that is also something which we get. This as standard Brayton cycle or the as standard Joule cycle, the working substance is essentially air. We can assume air to be an ideal gas. So, if we assume air to be an ideal gas, we can write these enthalpies, whatever we have here, in terms of Cp and temperatures. So, if we assume also that Cp is constant, then we have H is some Cp into T. So, we have Q out is H4 minus H1, which is essentially Cp into T4 minus T1. We have Q in is H3 minus H2, which is Cp into T3 minus T2. So, that is essentially what we have. And if we have an ideal gas, what we can also write is that we can write the pressure ratios in terms of the temperature ratios. So, we have pressure ratio is essentially temperature ratio for an adiabatic process. So, we can write P2 by P1 is T2 by T1 to the power gamma by gamma minus 1. Similarly, we can write P3 by P4. So, 1 to 2 is an adiabatic process, which is why we are able to write this. 3 to 4 is an adiabatic process. So, we can write also P3 by P4 is T3 by T4 to the power gamma by gamma minus 1. And we can also write, we can see that the efficiency, if you simplify this a little further, you can take out T4 and T3 common and do some little jugglery around, and we find that the efficiency comes out to be essentially 1 minus T1 by T2. So, essentially what we see is that the efficiency turns out to be just the ratios of the temperature at the beginning and the end of compression. It is linked to the ratios at the beginning and the end of compression, which is also similar to the expression which we get in a Carnot cycle. In a Carnot cycle also we see that the efficiency is essentially 1 minus T1 by T2, the temperature at the beginning of compression and the end of compression. But what we see is in the Carnot cycle, this would be actually rectangular. In this case, it is a cycle which is non-rectangular, but the efficiency is given, is still determined by just the compression process if we have ideal gases with constant specific heats. And this is also written in terms of the pressure ratio in this form. That is also something which we can see. What we see is when we find out these expressions from PV to power gamma equal to constant, which is for an these are essentially got from here, and the ideal gas relation, we have these from here. We see the pressure ratio is temperature ratio to some power here. Gamma is typically 1.4 for air, gamma minus 1 is 0.4, gamma by gamma minus 1 is 1.4 by 0.4, which is much greater than 1. We see that the pressure ratio is higher than the temperature ratio, which is something which is commonly seen in all of these things. So, for example, if you have the temperature doubling, if T2 is 2 times T1, the pressure will be much higher than twice the initial pressure. So, that is something which you see. So, pressures change by a lot, the temperatures do not change by so much. Just as a sort of curiosity, we can look at what would be the theoretical efficiency for different pressure ratios. So, we have the expression here 1 minus T1 by T2, which is also linked to P2 by P1. So, what we see is that as we keep increasing the pressure ratio P2 by P1 or T1 by T2, we have an increase in the efficiency. So, we already saw in the case of a Carnot cycle that the efficiency cannot be 100%. The efficiency depends on the ratios of the temperatures at which you reject and have heat added. In a similar way, in this cycle it depends on the pressures. So, you see that if you have a pressure ratio of about 10, the theoretical maximum efficiency you can have is less than about 50%. As you go to a pressure ratio of say 45 or so, we are somewhere around 65%. As we go to beyond 50, we get close to around 70% or so. So, if you look at data from on different actual engines which are there, you see that people have been trying to increase the pressure ratios of the engines which are actually running on aeroplanes, so that we can get to higher efficiencies. So, in the 1970s, for example, you see the pressure ratio was close to 10. You see in 2000, for example, the pressure ratio is closer to about 40 or so. So, this is about the Brayton cycle, which is used for gas turbine engines. So, we will maybe go on to looking at a problem dealing with the Brayton cycle. Thank you.